Physical quantities are fascinating. They're the measurable properties of materials and systems, like length, mass, time, temperature, and speed. Imagine trying to build a bridge without knowing how long it needs to be. That's where the International System of Units, or SI units, comes in. It's the universal standard for measurement, ensuring everyone is on the same page in science and engineering. SI units are categorized into three types: base units, like meters and kilograms; derived units, which combine base units, like speed measured in meters per second; and supplementary units, now part of derived units. This system keeps our measurements consistent and reliable, making it essential for innovation and communication across the globe. Base units are the building blocks of measurement, essential for understanding our world. We have 7 fundamental units. Length is measured in meters, the foundation for distance. Mass is in kilograms, crucial for weighing everything from a feather to a car. Time ticks away in seconds, the heartbeat of our daily lives. Electric current flows in amperes, powering our devices. Thermodynamic temperature is measured in kelvins, key for understanding heat and energy. The amount of substance is in moles, vital for chemistry. Finally, luminous intensity is measured in candelas, illuminating our path. Together, these units create a universal language of science and technology. Derived units are fascinating because they combine base units through mathematical operations. For instance, area is measured in square meters, or M2, which is simply meters multiplied by meters. Then there's volume, expressed in cubic meters, or M3, representing meters multiplied 3 times. Speed is straightforward. It's meters per second, or m/s, showing how distance relates to time. Force is defined as a Newton, symbolized by N, which breaks down to kg/m/s2, linking mass, distance, and time. Pressure, measured in pascals, PA, is force per area, or Nm2. Energy, captured in joules, J, combines force and distance, while power, in watts, W, tells us how quickly energy is used, expressed as Js. Finally, electric charge is measured in coulombs, C, which is the product of current and time, As. Each derived unit tells a story about the relationships in our physical world.
Supplementary units, once a separate category, have now officially merged into derived units. This change simplifies our understanding of measurements. Take the plane angle measured in radians. It's fascinating how a circle's arc length relates to its radius, making radians a natural fit for angular measurements. Then there's the solid angle, measured in steradians. Picture a sphere. The steradian helps us quantify how much of that sphere is covered by a given angle. This shift not only streamlines our measurement system, but also highlights the interconnectedness of these concepts in physics and engineering. Embracing this change enhances clarity and precision in our scientific communication.